Hello, everybody. Please welcome to this afternoon session. And please help me welcome Natalie Schaworonkow, who will tell us everything about spectral and time frequency analysis. Thank you. Welcome, Natalie.
Okay, hi. Thank you for the organizers for organizing this very nice workshop. I have the opportunity to talk about these two very interesting topics, but I have only like a very limited amount of time. So I selected some of 4 concepts so that people who have never heard about this stuff or just starting out get some intuition. And I've included a lot about like how to interpret the output. So let's dive into it. So for spectral analysis, what you might have is a signal like this. So this is the most beautiful rhythm in the human brain. Changed my mind. It's the somatosensory mu rhythm. And here we don't have a task. It's just resting state. There are no event markers. So what do we do with it? So we want to kind of like arrive at a summary measure that quantifies that the fact that we see some very prominent oscillations here. So people had the idea to apply something that's called Fourier transform to such signals. This idea already came up 90 years ago. So the idea came very intuitively, apparently. So what we want to do is we want to change from the time domain to another domain, the spectral domain. Why? We want to reduce the dimensionality of the signal. So instead of our many data points across time, we reduce our data to a few data points, only a limited amount of frequencies. So for instance, for EEG, we would only look at, I don't know, 1 to 50 hertz, for instance. Sometimes you have a strong intuition what frequency band would be very interesting for your analysis. So maybe you can just reduce the number to 1. Which you then can easily compare across conditions. So what is happening with this method? So here you see a small portion of a signal. So imagine this is a small snippet, just imagine it to be infinitely long. What we do is we try to see how such a signal is captured by a set of basis functions. And the basis function we choose here are sinusoids. So this is the end result that we will get. So this signal is composed of an oscillation with 1 hertz and a smaller contribution for an oscillation with 5 hertz. So just a small synthetic signal. So we first check for the 1 hertz, and we check whether we compute the dot product of our signal with a 1 hertz sign, and we get a value. If you don't like the word dot product, you can also say like similarity measure. So just how well the signal is captured by this sign. So you get a value, which you then can plot on this, for the moment, strange looking plot. And we plot this value on the x-axis. So step 1, step 2, we do the same thing, but we use a cosine. And you see that this cosine does not capture the signal so well. It doesn't follow the trajectory of the data points. So it has a smaller similarity value than our sign. So this is a This is our Y value. And then we can use these two similarity values that we obtained to plot this as a 2D point. So with the sign on the X and the cosine on the Y axis, and we get 1 point, and we can measure the distance from the origin of this point. So we measure the length of this little orange arrow that I plotted here. And this length of the arrow will give us the coefficient. So how well the 1 Hertz sinusoid captured our signal. Okay, so we can repeat the same procedure with a 1 Hertz, a 5 Hertz sine, and we get another value. We can plot it, and we can do it with a cosine. And again, we obtain a value that can be plotted as a 2D point for which we can measure the length, the distance to the origin. All right, so we will arrive at our notion that our signal is composed to a large degree of a 1 Hertz component and to some smaller degree of a 5 Hertz component. This is just a small synthetic signal, and I left out the other frequencies here because they would give us, for an infinitely long signal, they would give us 0 similarity values. Okay, but if we use now as basis function all available sinusoids of all available frequencies, we can then see how well our signal could be approximated by all of these basis functions. For every frequency, we can arrive at the power or amplitude of the basis function, and we can also arrive at the phase by extracting the angle between the orange arrow and the axis. All right. So this angle would tell you if you would kind of like shift your sinusoid into some direction, it would, what is the optimal angle that would capture your signal the best? Okay. Okay, so let's see. First, I talk a little bit about Welch's method. So in the previous example, the signal was infinitely long. Usually we don't have that luxury when recording real data. So what is typically done to deal with all kinds of noise is to compute the spectrum for small segments of the data, and then shift like the window we look at, with which we look at our signal a little bit, and then compute the spectrum, and then repeat it a number of times, and then average all of these different spectra that we obtain. All right. So we are averaging over the different segments. So this is called Welch's method. Before computing the spectrum, the signal is typically multiplied with a window function, a taper. I will come to that in a short moment. But first, let's look at how this signal above might show up in such a representation. So the raw values that you get from this from Welsh method may look like this. So for every frequency, there's a data point that tells you how strong this sinusoid in this frequency band contributes to your signal. What we often do is we plot this coefficients in a log Y scale, and you can see that it emphasizes certain aspects of the spectrum. What we can also do is we can adjust the x-axis, and you can see that it emphasizes another part of the spectrum. So let's talk about this in a bit. So at first you notice this very prominent peak in the spectrum, and that reflects our main oscillation that we can see very nicely in the time series. But there are also values at all these other frequencies. So does that now mean that we have different oscillations in the brain? So one here, and this could be then related to some cognitive function, just a specific frequency bin? I don't think so. So let's see how all these positive values at each frequency bin arise. So this I just found on the internet. It's a very specific categorization of cognitive function and frequency. I don't know. So the first thing to note maybe is that oscillations are very variable across participants. So here I plotted 6 participants. This is just resting state data. And you can see that the prominence of the peak varies quite a bit. So this is the representative participants, of course. So the peak is quite prominent. And here are kind of like more the average participants, where the peak is substantially smaller. So remember that this is kind of like in log space. And there are some participants for which we cannot really identify a peak in this frequency range. But there's still some signal part remaining. So what is remaining, even if you don't have an oscillation, is the 1/f component of the signal. So that's a quite prominent part of many biological signals. So if you take away the oscillation and just focus on these frequency bins, you will see that the power scales with frequency. So if the frequency increases, the power decreases. So, and you can describe the decrease in the frequency as a 1/f. In a 1/f description, 1/f with some kind of exponent. So it could vary how fast this frequency decay is happening. So here you see different simulated signals, and you can see that there's no dominant oscillation in these signals. There's a little bit of up and down, but there's no like dominant oscillatory processes going on, which you can immediately identify as a very pronounced oscillation. All right. So an example from the human brain. So this is the EEG of a 2-month-old baby. and this is an adult EEG. And you can see that the adult has this prominent alpha oscillations, which the infant totally lacks. But the infant will still have some power in these frequency bands. Okay. So in the EEG, MEG world, there's this notion of canonical frequency bands. So you typically divide your spectrum into specific regions, which you then give some funny names. So for the alpha frequency band, it would, for instance, be 8 to 13 hertz. But for this signal, for instance, in this alpha frequency band, there is no prominent oscillation occurring at this point. And similarly for the baby, it has some alpha, it has some activity in the alpha band, but it's not an oscillation. So you have to be kind of careful here. So I think what I want to illustrate with this point is that the method, the algorithm will give you some number, but the interpretation of what the signal is has to be made by you. I also want to highlight that these canonical frequency bands may not capture things perfectly for every participant. So in the blue, you have a participant which has a spectral peak fitting exactly in the canonical frequency range. And these frequency ranges you would, for instance, use to define filters and filter in a specific frequency band. And here you see a participant in green where the alpha, like the spectral peak is occurring a little bit earlier. So some of the energy is outside of the canonical frequency range. So if you would now use the canonical band to filter your signal, you would arrive at different spectral powers if you average over these frequency bands, even though the signal energy is the same for both signals. Additionally, for instance, what would show up here is that if you filter in the little bit lower frequency range, the theta frequency range, the green signal would give you an elevated theta. Even though maybe neurophysiologically you would say there's no theta going on here. There's no theta rhythm, pronounced theta rhythm here. Okay, so this was a little bit about the height and place of the oscillatory peak. One prominent feature of physiological neural rhythms is that they show some amplitude modulation. And this will influence, this can influence how wide the spectral peak is. So let's look at an example in synthetic data. So here I simulated a super simple sine wave. And you can see there's a prominent, almost like singular peak, delta type peak in a specific, at a specific frequency bin. And then what I will show you now is I use a function to amplitude modulate the signal, so to systematically modulate the amplitude by multiplying these two signals together. Again, this shows like a very small segment. You can imagine that the signal continues outside of the edges. So if you amplitude modulate the signal with this specific function, what happens in the frequency domain is that your spectral peak will get broader. So for the nerds, multiplication in the time domain is convolution in the spectral domain. So you can see that as I change the width of my amplitude modulating function, this spectral peak gets broader and broader. So here I chose a special function which has like a boxcar shape in the spectral domain. This is a little bit of an exaggeration, so it will not look like this with real data. But you can see that like the amplitude modulation is also present in real data where neighboring cycles have similar amplitude. So there's a slow fluctuation going on. You just look at the amplitudes. All right. There's another curious phenomenon where you see additional spectral peaks. So what does it mean? If this peak now occurs at the beta frequency range, is this now a beta rhythm? We cannot tell from the spectrum alone, I would say. So here I show you a synthetic signal that I simulated. And what I did was to vary the strength of the higher frequencies. So these signals are simulated by summing together sinusoids with a fixed relationship. So, and you can see that if I increase the spectral power of my harmonic contribution, the time domain signal will change its shape from being a sinusoid to being, I don't know, saw-tooth-like. So these things are linked. So if you now look how oscillations look like in the wild. So here's an example from ECOG, just that you can see it really easily, that you have this really sharp troughs and a really broad peak phase. And you can see that this will result in strong harmonics that will show the amount of energy needed that is needed to reconstruct this signal in such a way. So again, I want to conclude that if you see several spectral peaks, it does not mean that you have like several individual oscillations going on. You can check in your time domain how the signals look like. If they look like this and they exhibit like a very strong relationship, if these rhythms have a strong relationship to each other in terms of fixed phase shift, for instance, they are probably not independent physiological entities, I would say. Okay. So Robert told us already in the morning that the EG or the MEG is comprised of many different types of signals that are mixed spatially across space. So here I plotted a few examples of independent rhythms. So you have, for instance, frontal theta, occipital alpha in the back here, and several mu rhythms for both hemispheres. So there are different oscillations present in the human brain. And these you see that there are different oscillations, even though they are in the same frequency band. So what we wanted to illustrate a little bit, that if you look at your spectrum from a specific electrode and you observe a spectral peak, the peak could also come from a region that is far, far away from the electrode. I don't know, I have a little bit of time, so I explain this psychedelic plot. So here, this is a simulation. So here we placed a few alpha rhythm type sources into a human brain. And then we calculated with the help of a lead field how much each source contributes to each of those channels. So you can read these little pie charts as contributions to the signal variant, to the signal power in the alpha band specifically. So if I make the posterior rhythms very strong, for instance, this could happen if the participant closes its eyes, the alpha rhythm gets very strong. This signal content will also be visible in the frontal electrodes, okay? So if you take a frontal electrode and you observe an alpha peak, it might not be generated in the vicinity of the electrode, just because how the signals propagate through space. So this is a little bit of an extreme case, just to illustrate this. It's in the special issue that Max talked about yesterday. So there are many interesting articles in there. Check it out. Right. So even though if we have a spectrum and we compute it for like we don't take space into account in this plot or like in the previous plots. We are still kind of like in space. So if you do, for instance, your spectrum across all electrodes, you might find a quite complicated pattern with many peaks and different types of dynamics depending on location, because of the spatial mixing of the signal. So that's why you should pay attention tomorrow in the source estimation lecture and in the hands-on. All right. So obtaining the power spectrum is super easy nowadays. You don't have to program punch cards. You don't have to cut out paper and align it manually like in the old days. You can do it with one line of code, but the work is not done yet. So you get some numbers and you have to, it is your job now to relate them to like physiologically valid constructs. So you need the careful interpretation to make valid conclusions. Okay, so that's a bit about interpretation. Are there any questions so far? It feels a little bit weird, everybody's so quiet, so.
Hello. For the WETS method, you say that you divide the signal in different segments and then take the average, the mean of what? Of the power spectral density of each segment?
Yes.
Okay.
Yes.
And I get another question. Maybe trivial, but neuroscience is new for me. When you talked about canonical frequency bands,
Mm-hmm.
are they arbitrarily chosen or from the experience? Or do you choose the range of frequency of the canonical bands?
So the canonical frequency bands are given to you by your elders, and they disagree. If you look in the literature, there's a little bit of wiggle room, what people like consider the canonical alpha band. It could be like, I don't know, 8 to 12 hertz. It's like empirically derived frequency ranges. So has been observed in the clinic, for instance, some of these bands. So this is just like canonical in the term of like, this is what our literature apparently agreed on, our research field. It's not like a priori derived.
Okay, thank you.
Thank you for the presentation. I have two questions. First is what is the interest of looking at log graphs when we do this transformation, actually, spectral transformation, log to log graph or log of power or log of frequency?
So if you look at a spectrogram of log frequency, you will see this as a nice linear relationship, the 1/f. So if you're interested specifically in the 1/f component of your signal, you can then like easily estimate this part of the signal. And the y-axis, I think you need to look at it in log power, because otherwise you cannot see many of the subtleties that you would otherwise like for instance, the small peak is not visible at all here. So it's to highlight all of these different components better.
Thank you. And for my second question, actually, if I'm not mistaken, we can calculate the spectral power with wavelet methods as well.
Right.
And what is the difference between this Fourier transformation and wavelet method for calculating this power spectrum, and also power to frequency bands, and also we can have different results. How can we interpret this?
Right. So hold on to your question. I think I will now present a little bit of more method relevant things, and then we can come back to it. All right. Okay, maybe one last question. Okay. No? There was okay. There was a question in the back next to you, but disappeared.
Thank you. Again, maybe a little bit naive, because I mean,
Naive is good.
Okay. I was just looking at the differences between children and adults. So let's say you're doing a study and some of your participants are a little bit younger than the other ones. do you have individualized alpha peaks, for example? Because obviously you'll be different
Yes.
depending on the age. How do you deal with that is the question.
So you allude to a very prominent effect that is occurring across development. So the frequency peak in the alphabet, or like the alpha frequency, the alpha rhythm frequency changes across development. So that's like one super stable effect, one of the most stable effects in the oscillation world, I think. And I would say you need individualized frequency ranges, otherwise it makes no sense, because you will not capture the effect that you want to capture with the canonical bands in the development. Okay, so there were already some questions about more method stuff, so let's check. Oh yeah, here. So as always, there are a bunch of parameters that you can vary when doing your spectral analysis. So one important point is number of frequency of Fourier, like the number of points that you use to estimate the spectrum. If you have more points, you can per segment that you use, you have less opportunity to divide your signal into segments. So the more points you use for an individual segment, the less segments you have. Then there's a thing called taper. We can talk about it in a bit. All right, so, and there are some other parameters that are easily accessible to you when you run your power spectrum computation. Let's check them in a little bit detail. So I already gave some disappointing answers to people who asked me this question. So what are the correct parameters? There is no size fits all, so it depends really what you want to do. So you see, if you work in development, you need to adjust your alpha frequency ranges. While for adults, I would say it's quite stable, quite robust. You may not have the need. So the starting point is the parameter set that maybe your PI gives you or you obtain from the literature. But as previous literature has not solved the brain yet, this is not set in stone. So what you should do at some point when you feel confident enough is to change the parameters and observe what kind of effects that has on your data. And the effects you want to obtain from your data should be robust for similar parameters. So this is called sensitivity analysis. And you will soon figure out what the crucial parameters for your own work are. I could give another lecture how simulation is useful for building intuition in these things, but not today. Okay, so what we need to have for our estimation is a number of points that we compute the spectrum of. So if we have a short segment of 1 hertz, a short segment length of 1 second, the slowest sinusoid we can fit in there with a whole period is 1 hertz sinusoid, okay, without any kind of traces. And we can, of course, fit all the multiples of that. So a whole period of these sinusoids will fit into a segment of a 1 second length. If we increase our segment length to 2 seconds, we can also fit a slower sinusoid in there without any residuals. So it will cover a whole period of a 0.5 hertz. So if we increase the segment length, we also increase our frequency resolution. If we have a super short segment length of 0.1 seconds, the slowest oscillations or slowest sinusoid we can fit in there is a sinusoid with a period of 0.1 seconds. That's 10 hertz. So our frequency resolution gets very poor if we have only a very short segment length. So let's see a demo of that. So here we only have 0.1 seconds available of data for each segment, but we have a lot of segments. So we chopped up our data in very short segments, and this is the resulting power spectrum. It looks very sad because you cannot see anything. Okay, let's try better. So we increased the number of samples per segment, and you can see that the frequency resolution increased. But we have less segments. Okay, let's increase the number of segments some more. Oh, the peak is emerging. Okay, so you have managed to see a alpha peak with a segment length of 1 second. So here the frequency, sampling frequency is 1000. Okay, if you increase the number of segments a little bit more, you can see some other phenomenon. So you can see that there's like a double peak here for some reason. And you can see the smaller peaks emerging a little bit better, I think. Okay, so now we have segments that are 20 seconds long, but we now have only few of them. So you can see that the noise increases because the objective of this averaging across segments was to reduce noise. If we don't have so many segments, we have more noise. Okay, so it's getting scary. So only 5 segments to average over, but a lot of frequency resolution. And this is what happens if you have only 1 segment. So the noise takes over. So the power spectrum of like the power for neighboring frequency points is varying widely. So that's why you get this up and down jumps, which my plot does not show in a super nice way. So it looks like a band, but it's actually like going up and down. So what is the correct resolution that you would choose? So maybe something in the middle. All right. It depends on what you're interested in. If you want to average over the alpha frequency band anyway, you would not care about I don't know, having these subtleties of the peak. All right, so that's about frequency resolution and number of segments. Okay, so what about these tapers or windowing functions that I mentioned? So if you cut your signal into segments, it may happen that your segment length does not capture a whole like a the signal like a whole number of cycles of the oscillation. So there's one little part that is a little bit left over. So there's another cycle beginning. And this will cause edge effects, because if you imagine you fit this signal with a sine, it would fit perfectly except this part, okay? And for this part, you would need additional basis function to fit it properly. So to deal with these edge effects, edge artifacts, we use a taper. So for instance, what is this? Hahn window. So you multiply your signal that you want to get the spectrum off with this window. So, and this will attenuate the signal on the edges to 0. Okay. So this is the resulting spectrum for the signal that was not windowed. So if you are not windowing, you can see, say you are multiplying it with a boxcar function. That explains the label here just. So you see, even though the signal was kind of like a perfect sinusoid, so it should have only, in our spectral analysis, should have only like one spectral peak that is just at the frequency of this the signal. You have some so-called spectral leakage. So you have also power at neighboring frequency bands. And you have more power at these neighboring frequency bands if you don't use a window function than when you use a window function. So that's why you should use a window function. Okay, because you don't want to capture these edge artifacts. Okay, so so there are different approaches for selecting segment length. I just want to briefly mention that. In all the previous slides, we used the same kind of like segment length per frequency. But you can also adjust this a little bit and have a dynamic selection. I think that's actually more relevant in the time frequency analysis. So let's skip this for a bit. There's also another approach which there was a question about. No, it was about wavelets, the question. Okay, but here, this is the multi-taper approach. And here you use different, a number of tapers. So here you use more averaging to increase to decrease the noise. So here, what you do is you use a number of tapering functions that are smartly chosen, multiply your data with it, and then obtain the spectra and average across all of these tapers. Okay, and you could, for instance, also, so this could be, for instance, combined with doing this for each segment. Okay. So this is just to give you basically a Google keyword So there are many different approaches, and which one you need is dependent on what you want to achieve, basically. Okay. In this slide, I just want to briefly mention that there's also the other side of the coin. So here you have two signals which look a little bit different in the time domain, but in the spectral domain, they will be identical, because the only thing that is changing is the phase across. The phase relationship between the different frequencies. Okay, so just to briefly mention that the power spectrum only captures a part of the available information. And the other part is contained in the phase spectrum. I think you typically don't look at it so much when you do just spectral analysis, but we will come back to it in the time frequency part. Okay, so just a word cloud about some of the concepts that you heard. The choice of parameters depends on the analysis goal. Very important. The most important thing I can say probably for regarding parameters. And the other important thing that I can say is that you get the numbers, but you still have to do some work in terms of interpretation. That's often like a much harder than programming a script that runs your frequency analysis. Okay, so that's about spectral analysis. Okay, so what does the time frequency mean here? I just told you we need to do a dimensionality reduction to get rid of the time. Why do you want time back? In averaging over collapsing over time, you assume that the characteristics of your signal don't change across time, but they will do in lots of cases. So here's a power spectrum for two signals. It's essentially the same power spectrum for both signals. Okay, so the first signal is a non-sinusoidal rhythm, which has also some contribution from a harmonic peak. And the other part is a pure sinusoid type of rhythm and a faster rhythm. Okay, so you will not be able to distinguish between those two cases if you just average over time. Okay, so quite often you are also specifically interested in looking at the temporal dynamics across trials. So this is just a very simple task. Just open your eyes and you can see that the rhythm that you have attenuates if the participant opens their eyes. So you could, for instance, compute the power spectrum for this part and for this part, and you would arrive here and you can then quantify the differences. But often you are interested in like capturing the kinds of how fast does do the temporal dynamics change. So that's why you need to preserve the time. And that you can do with a time frequency representation. Okay, so you can do this with different methods and they give you similar results. So this is, first is short-term Fourier transform. So here's essentially your signal, and you do very analogous what you did in the Wells method. You slide a window over the signal, you taper it to attenuate the edges, you compute the spectrum, and the only thing what is the difference is you don't average. You kind of rotate your plot a little bit and put this these numbers you color code and put in as the y-axis, and you do that for every segment of the data. Okay. So what is the difference to wavelet? So I only have like one slide to wavelet, which is I don't know, a shame. So wavelets are specific kind of functions. So they are created by multiplying a sinusoid with a Gaussian. So they have this specific profile in time. And what you do is you go through your signal, and then you check kind of like how similar your signal is to this wavelet. And what you vary is, for instance, you vary the frequency of the wavelet, and you vary, for instance, the attenuation of the wavelet. These are your parameters in this case. So just look at, we look at some examples, how it looks like. So here's maybe one time frequency representation that you can observe in a way. So I just picked an interesting one from the literature. If Max would be there, he would scold me for JET, but JET color map. JET party, okay. So here you can see this is an average over trials, and what the participant had to do was to perform a movement, and the 0 here is the termination of the movement. And you can see that there's a rich set of complex stuff going on. So the mu rhythm in the 10 Hertz frequency band is attenuated relative to a baseline. And we also have this beta post-movement rebound effect, where the beta band activity is elevated after the movement has been terminated. So to obtain a figure like this, what you need to do is you calculate the signal relative to a baseline, or you need a normalization procedure, or you do a contrast between conditions. So that's what you typically do. Very similar to what you already done with the ERPs. Just that it's now in 2D and in more colors. All right. Okay, let's see. Okay, about parameters. So these are different. These are time frequency representations that were obtained with the short-term Fourier transform and the wavelet method. And I would say these are kind of like default parameters. And now what is shown on this side here is a zoom in into this region, and the parameters are varied. So this is length of the segments are varied. And this is number of cycles of the wavelet are varied. So, and you can see that it has a systematic influence on the appearance of the time frequency representation. So if you decrease your segments, you get a high uncertainty in the frequency range. Okay. Just as we discussed before. If you increase the number of segments, or increase the number, the number of samples in the segment, what you get is an uncertainty in time. So you either get horizontal stripes or vertical stripes, and some blobs in between. So again, it depends on your goal in the analysis, what kind of parameters would be important to choose for you. If you care about higher frequency ranges, maybe the temporal resolution is not as important as if you care about lower frequency ranges, because the higher frequency bands all kind of behave in a similar way across frequencies, which may not be the case for these lower frequencies. Okay, so it depends on the physiological phenomena you are interested in. Okay, so this is a little bit about the phase again. So all previous plots were related to power, extracting power or amplitude of the signal. You can also extract the phase. So what is plotted here is, just to illustrate the measure, a number of trials and the signal across time. Okay, so the signal is slow varying sine wave, and what is shown here is the phase at this specific moment in time. Okay, and you can see that all the trials are kind of aligned and have the same phase, and that's when this intertrial coherence, which measures the phase coherence, has the maximum value. Okay, now we can change the alignment of the trials. And as we change the alignment, each trial has a different phase in time at this specific time point. And what we do then to get the intertrial coherence is we add up these different phases together. Okay, if all the phases are the same cross trials, it would give us a high number. If it's all scattered around, the phases of different trials will cancel each other out. So this will be a small number. Okay. So let's see how this looks like in neural data. So this is just stolen from EEG lab documentation. So here you have the power in the time frequency representation, and here you have the intertrial coherence. And a typical picture that you will see is that intertrial coherence is large for these very low frequencies. And what this will capture is it will capture the ERP. Okay, so if it captures the ERP, maybe it's better to look at ERPs directly if you're interested in this specific aspect. So maybe what is when it's more interesting to look at this measure is if you compare two different trial groups, for instance. So this was an experiment where the participant was stimulated with TMS, and then over the visual cortex, and then had to report, did I observe a phosphene or not? So it was a behavioral report, and the trials were split into these two groups of categories. And then what was compared in this plot is we compare the intertrial coherence across the trials where the phosphene was seen versus the phosphene was not seen. And we can see that what we can see with this difference is that if the simulation was applied at a specific phase of rhythm in this frequency band, it's more likely that the participant reported that they had seen a phosphene. So in that way, you can assess excitability. Does the oscillation phase modulate excitability? So that's quite interesting. At this stage, your data should already be cleaned. So, but still I want to highlight that also different artifacts have specific representation in the time frequency plots. So here you can see a signal, very regular alpha rhythm, which will show up here. And this is the same signal, just with a single spike added, okay? And the single spike will show up as an increase in power across all frequency bands, okay? So, so this is just how this artifact may be represented. They could be slow drifts, and slow drifts would show up like this in your time frequency representation. So increased power in the lowest frequency bands. And muscle noise would show up as increased power in the higher frequency ranges. So don't misinterpret that as gamma oscillations or gamma rhythms. It's always informative to go back into the time domain and check if I cannot make sense out of the time frequency representation, go one step back and check in the time domain, because there it's sometimes easier to figure out what's going on, for instance, in this case. Okay, time is running fast. Let's see. I have like one more slide maybe. So again, this point about interpretation. So here, if time frequency representation is derived for this evoked response, auditory evoked response. The time frequency representation will show up a peak in the 10 Hertz range, for instance, because of the dynamics of the ERP. The time frequency representation itself will not tell you about like the generative mechanisms, how the signal was generated. So whether it's like a oscillatory rhythm or whether it's an ERP, that's not what the method will tell you. The interpretation has to be made by you. And that's often like quite tricky, and there are ongoing debates about that. Okay, let's skip to this slide. And then maybe we have some time for questions also. So here are some concepts which I could not cover in detail, just gave you a flavor, hopefully. If you want to know more, there's this amazing resource from Mike Cohen, his YouTube channel. You can watch the videos. It's amazing. He starts off really gentle. So even if you don't know like what a complex number is, he will explain it to you in a very nice way. And now we can play a little bit in the hands-on and discuss more about this concept. All right. Thank you.
Thank you, Natalie.
Question?
Yep. Thank you so much, Natalie. Are there now any questions? The topic is quite heavy, so there are probably lots of interrogations right now. There was also one over there. Yeah. Yes, please.
Hear me? Okay.
Yes.
Thank you so much for the talk. I wanted to know, when you're talking about the tapering windows,
Yes.
if you increase the tapering windows, does that offset spectral leakage?
If you increase
The number of tapering windows you have when you're segmenting the data, does that help offset spectral leakage? Or when you were talking about amplitude modification, or excuse me, modulation, does that help with managing spectral
so
leakage?
increase the number of windows, you mean like in a multi-taper approach?
Yes.
Yes, it will change the spectral leakage. Depends on like the windows, like how you chose the windows and so on, and the bandwidth of these windows, but it will affect us, yes.
Okay. Thank you.
Thank you for the presentation. So I wanted to ask about this picture where you are showing this bimodal peak that appears when you change the number of samples and so on. So I wonder, when you see this kind of bimodality, would you expect there will be like two subsets of trials in such that in one subset you have one sub peak and in another one you have another second sub peak? Or it actually can happen that you can have even small subsets, like you cannot really distinguish on the level of different trials. So like in every trial you would have two subpeaks.
Right, so you're talking about this,
Yes,
right?
yes.
So in this, I can tell you, it's a mu rhythm that contributes to the later peak and an alpha rhythm that's more occipital and that contributes to the earlier peak. So it's like spatial mixing here. It could also arise in different ways. It's known, for instance, that participants get tired during the course of your very boring experiment, and then the alpha frequency slows down.
I see. So you cannot distinguish them.
So
on
there
trial
could be
level.
these changes across trials. And if you average over time, you cannot really know where this comes from. You have to like check the peak in a more like trial-based analysis, maybe. So it's possible. Does that answer the question? Yeah, okay.
Can I ask a question? Thanks for your talk. So you say from the beginning and then also afterwards that it's a way to compress the time signal to pass to the PSD, and then we can add the time again in the time frequency part. And so is the PSD plus the phase enough to represent all our time signal?
So you mean if I like
You
if
showed
I
before that it was changing, no? You have one signal in the time and then another, and then you have the
right
spectrum.
like if you have all the frequencies available and all the all the phase information also, like if you have like amplitude and the phase for all frequencies available, you can perfectly reconstruct your time domain signal with like inverse Fourier operation.
Okay.
So it captures all information that is available in the time domain signal in some aspects, but you have to look at like what aspects you are specifically interested in.
For instance, if we want to feed a machine learning algorithm, so we want to have the most information available, would you feed it with a power spectral signal or with a time series?
It depends what the objective is.
Classify,
yeah.
depends on the data set.
Um,
But you want to maybe classify the mood, the motion. You want to classify motion. There is a subject watching videos and you want to classify motion.
yeah, in the way, like as the information is present, in both presentations the same way. You can use either of them, but like practical considerations may result in like you preferring one approach versus the other, but I don't know.
No, yes, this is one way. The practical thing is, I understand, but ideally is like the power spectral taking all the information of the initial time that was.
Yes, if you
defined.
preserve the
Okay.
phase, yes, I would say yes.
Okay. Thanks.
First of all, thank you very much. That was really, really helpful overview. Here a very basic short question, but I think it's a practical one. What is the proper unit to put on my plots for power if I run an FFT, if I run a wavelet convolution? When is it watt squared? When is it watt squared per hertz?
So it depends on like the toolbox you use and the parameter setting that is employed. So some like MNE, if you put in like a normalization, you want to normalize versus, I don't know, frequency bin width or something like that, then you put power spectral density and then it's in specific units. Like the units will kind of like scale down like the y-axis, but it's, I don't know, usually you are not so interested in the absolute units, I would say. Are you?
No, I'm not, but I mean,
So
my supervisor asked me, and I mean, I don't want to embarrass myself in publishing a paper with wrong
so
units.
often I put AU arbitrary units.
I've seen, and I've done the same, but I've been called out by my supervisor.
Okay, I think you can also put, I don't know, what's your favorite unit?
I don't know, like, yeah. It's a tricky topic, and people keep asking this question. And so my most recent answer was, look, you don't really care, because down the road, what you're going to do is compare those amplitudes, whatever scale they are in several conditions. And so this unit doesn't matter. Now I understand it's not really a very satisfying question, but as a matter of fact, in the various toolboxes, I don't know what you guys would reply, but it's often very hard to get down to finding out what the unit is of that time frequency transform or spectral density plot. Yeah, what they're all nodding.
Stick to AU.
So it's quite unsatisfying, but yeah, you put some microvolts or femtoteslas, and the square helps sometimes. And if you're really courageous, you put the /hertz. That also helps. That does have a meaning though. Yeah, it doesn't really matter at the level at which we're talking about. We're talking about running experiments to explore cognition, you know. And so at that level of interest, it doesn't really matter the underlying unit. If you were developing methods, that would probably be a very bad answer that I'm just giving you now. Any other question? Yes, in the middle here.
Quick remark about units. My supervisors also find them very, very important, because different amplifiers and different noise levels. For example, many have noise levels at 60 nanovolts per square root hertz. Some have 100, some have 10. And if you have the absolute units, then you can very precisely see how far you are away from the noise level, and whether you're actually measuring a brain signal or just amplifier noise. But that was actually not my question, it was just a brief remark, because the question just came up. And I wanted to defend putting the right units there. My question is about the multi-taper. From what I have read, it has a lot of advantages over Welsh, the Welsh algorithm. And the only disadvantage basically is that it's computationally a little bit more expensive. But given that our computers are getting faster and faster, shouldn't we at some point all use multi-taper? Does Welsh has any other advantages?
So I would say for like the lower frequency ranges, like 10, 20, 30 hertz, which is my interest, basically, it doesn't make a difference. You know, you get the same information that you would get from a multi-taper, and maybe you get like little bit weird looking spectral peak shape. I think that's why I don't like them so much, but it really depends on what you're interested in, I would say.
Thanks.
Thank you so much.